different types of symmetry figures can have. So I have at the start, this is just a, I don't know, fun fact about bugs, or animals, I should say too, that has to do with symmetry. So it just says, in the animal kingdom, the symmetry of an animal's body is often an indication of the animal's complexity. So animals that are displaying line symmetry, which we'll talk about, such as insects. So insects display line symmetry. You can draw a line of symmetry and see kind of at that reflection on either side. They are usually more complex than bugs or animals that don't display line symmetry, that might display rotational symmetry, such as a jellyfish, and we'll talk about what rotational symmetry is. So, I don't know, fun fact, but just an example too of where, I mean, we see symmetry all over the place, whether or not you think about it. Different objects that display line symmetry, rotational symmetry. We're also going to look at plane symmetry, axis symmetry, so different types of symmetry. So a figure has line symmetry if the figure can be mapped onto itself by a reflection in a line called the line of symmetry. So notice it's the figure being mapped onto itself. So in these examples, it's saying state whether the object appears to have line symmetry, yes or no. If yes, draw all lines of symmetry and state their numbers. So how many lines of symmetry that it has. And I know the lines are drawn in the first two to give you this idea. So here we have a crab, and you can see a crab does have line symmetry. If I drew a line here, and then I reflected the crab over that line, it would reflect onto itself. So this has line symmetry. I'm just going to put yes, and then I'll put 1. For yes, it has 1 line of symmetry. Example B, that is a starfish. And you can see, and this would be true for any star or star shape. I could draw a line here, and then that would map the figure onto itself, but you could rotate that star, and really through any vertex like that of that star, you'd have a line of symmetry. So there are actually 5 lines of symmetry through a starfish or through a star. Then in C, we have that seashell. Would you say that seashell has line symmetry? I see some no's. So the way to determine is, you have to think, if I drew a line through this, anywhere, would both halves be the same? Like if I reflected over, do I see that reflection? In this case, based on that shape of the seashell, there would not be. So this would be a no. So what I'd like you to do for those next 3 shapes, I'd like you to determine if they have line symmetry, and then draw in. So if they do, I want you to draw in all of the lines of symmetry. And you might even draw a line and then really look at it and realize, oh, it's not actually reflected over that line. So for D, E, and F, just take a couple minutes to determine if there's line symmetry. If there is, draw them in. How many lines of symmetry does it have? So you can walk around, and I'm going to tell you yes or no. I just want to give you a chance to think about it. right, I don't have the answers up here. Actually, I'm just going to leave that there. Maybe I'll just leave it frozen so it doesn't move. How many of you think D has at least one line of symmetry? Okay, so walking around, some of you said yes, some of you said no. Could I have somebody who thinks there's at least one, or if you think there's multiple, can somebody come just like over that object to draw in where you drew your lines of symmetry? Well, you're not the only two that said, well, yes. You're not the only group that said that. Somebody who drew in lines of symmetry for D. I'm not saying that you're wrong. I'm not saying that the answer is no. I'm not saying it is yes. I want to look at it if you drew in a line of symmetry to see if it really is a line of symmetry. Or actually just draw one of them. Okay. But through the corners. All right, we get it. Okay. So the question is, because I saw a lot of you had this line, or if you said yes, you had this line and then you had the other one also drawn in. And I want you to look at that and say, is it really reflected over that line? Isaac? I have another one. You have another one too? Yeah. Where did you do three? I actually didn't have those ones. Okay. But I had one going down the middle. Yeah, so it's like directly down below. So, okay, I'll have you draw yours in a minute, so I'll erase this one. So, if you look at this, would that really be symmetric? I'm hearing yeses and no's. What shape is that? What would you call that shape? Maybe it's a rhombus. Parallelogram, probably. What's true about a parallelogram? Two-thirds of parallel sides. What else is true about the sides? The pairs of sides. Opposite sides are congruent. So this side would be congruent to this one, and this one congruent to that one. So if you reflected, say, like this triangle over, these two sides should be congruent, and these two should be congruent. So this line would not be a line of symmetry. And I know that's an immediate thought. So a lot of you had that, and I had that thought too, is that one. But if you really reflected it over, this would have to kind of be rotated around. It had to be actually, if it was a kite, then a kite would be, or would have that line of symmetry through that diagonal. I think you want to draw yours. Yeah, I realize I don't think it works. I think I didn't picture what you said, but. Oh, yeah. So actually, when you said that, so this is what I said that, so we can just look at this. I had wondered, I said when you said that if that would work, but it's kind of the same reason. In a parallelogram, the opposite angles are congruent. So this angle was congruent to this one, and this to this one. So if it reflected, the congruent angles would have to be different. But it takes a little bit of picturing and thinking about it. That's why I just want to tell you the answer is no. There's actually no lines of symmetry for a parallelogram. All right, for E. So D, you should have no. Anybody find any lines of symmetry for E that would like to draw one? I don't want to do the drawing. I want to see what you have. Or are you saying there are? I'm Down the center. Someone can draw it for me. I'm going to ask for F2 if you have any for F. All right, so if we reflect that over, it's symmetric. Did anybody have any other lines of symmetry? Okay, so E, yes, there's only one. So there's that one down the middle. Anybody find any for F? Zero. If you did find more than one, you can draw all of them. All right, tag for F. So a rectangle. While a rectangle technically is a parallelogram, when it's a rectangle, there are lines of symmetry. There are two. So down the middle, but either way, vertically and horizontally. So this one is no. This one is yes. There's one. This one is yes. There's two. Any questions on lines of symmetry? It would not go through diagonally because for the same reason for this one, because if it went through diagonally, these two sides would have to be congruent to each other, and these two would have to be congruent to each other, which is not true in a rectangle. For a square, that would work. So only vertically and horizontally through the middle works for a rectangle. Thank you to those of you that came up to draw those. All right, then rotational symmetry. So this is another type of symmetry. This is where a figure can be mapped onto itself by a rotation between 0 and 360. It could be, or we'll talk about the 360, because everything, if you rotate it 360, is mapped onto itself. But it can be mapped onto itself by a rotation between those degrees about the center of the figure, called the center of symmetry. It is, or could also be called, the point of symmetry, so the center or the point of symmetry. So this gives an example of, this would actually be a square that's here, but it's just rotated to look like a diamond there. So if this is the original image, this is the pre-image, and it's showing that it hasn't been rotated at all. This is showing what it would look like if you rotated it 45 degrees. It would turn, and now it would be what you would typically look at like a square. If you rotate it a full 90 degrees, so a rotation from here to here, then that image looks the exact same as the original. So this is showing that there's rotational symmetry because a rotation of 90 degrees maps the image onto itself. You will also map this onto itself if you rotate another 90 degrees, so 180, another 90 degrees, so 270, and then we know if you go 360, anything maps onto itself at 360. So there's rotational symmetry in that figure. We are going to come back to look at this after we talk about the order and the magnitude. So symmetry, rotational symmetry has order and magnitude. The order of the symmetry is the number of times a figure maps onto itself as it rotates from 0 to 360. And then the magnitude is the smallest angle through which a figure can be rotated so it maps onto itself. And this is the equation that relates magnitude to order. So if you take 360 degrees divided by the order, that gives you the magnitude. So I actually want to flip back to the example we just looked at. So this would have an order of, so we said it mapped onto itself at 90 degrees, 180, 270, and then 360. So the order, in this case, I would include the 360. The order is 4. And that means then the magnitude is 360 degrees divided by 4, which is 90 degrees, which I can see that is the smallest angle of rotation that will map the figure onto itself. But there is that equation that allows you to find the magnitude based on the order. So the order is the number of rotations from 0 to 360 that can map it onto itself. The magnitude is the smallest angle. But again, you can take 360 and divide it by the order. So in these next examples, it says state whether the figure has rotational symmetry, yes or no. If yes, locate the center of symmetry and state the order and magnitude. You would not say, or you would say no if the only rotation that maps it onto itself is 360. So if that's the only rotation that's going to do it, then we say it does not have it, because that's true for any figure. So if I look at A, that hexagon, I'll help you out with this one. So I would say this does have rotational symmetry. If I put a point at the center, and I'm just going to draw, like, say this is my start here. I know that if I rotate this, kind of a rotation to the next vertex, so you have to kind of think if I twisted it, that, and I can find that angle, but if I had rotated it that much, it's going to look the exact same as when I started. It would just be, this side would now be here, this side would be here, this side would be here, and so on. So I could rotate it that much. I could rotate from here down to here. I could rotate basically to any of those vertices, and it's going to map onto itself. So I would say, yes, there's rotational symmetry. The order then, so again, if I picked, this was my starting point here, the order would be 1, 2, 3, 4, 5, 6. So I would count all the way back to the original. So again, 1, 2, 3, 4, 5, 6. And that means my magnitude is 360 divided by 6, and that is 60 degrees. And what that means is this first angle of rotation is an angle of 60 degrees. So if I go 60 and then I keep going 60 degrees all the way to 360, that's 6 rotations. That's why my order is 6. Questions on that? Okay, would you say this triangle in B has rotational symmetry? No. So the reason it's working for this one, this is a regular hexagon. All side lengths, I know it's not marked, but all side lengths look to be the same. Here in this right triangle, you can clearly see, well, it's a right triangle, so it's not equilateral. So this would be a no. There's no rotational symmetry there. What about in C? The answer is yes. There is rotational symmetry. So if you pick a point at the center, I look at this and I think of it as a flag. I'm not sure why. There's no picture on it, but I think of it as a flag. So if I put a point at the center, here's how to picture this. If I kind of think as this as my start, I could rotate that all the way to here. So I've kind of turned it, well, actually, what angle of rotation would that be? How far would you have to rotate it for it to map onto itself? What'd you say? 180, yes. So this would be a 180-degree rotation going around half of a circle. So if I rotate it 180 degrees, then I'm going to get back, I'm going to map the image onto itself. It's going to look the same. So yes, there's rotational symmetry. The order then would be 1, 2. The magnitude, the 180, that's my magnitude. 360 divided by 2 is 180. So the smallest angle you can rotate it to map it onto itself is the magnitude. I can go 180 and then 180 again. That's why the order is 2. And that brings me to 360. Okay, and then we have these two flowers, which these two flowers are not, you will not have the same answer for both of these. So would you say this flower has rotational symmetry? If you rotate it, it's going to map onto itself. So you'd have the center of your flower. Let's say this is kind of a starting rotation. What would you say the order is? How many rotations would map it onto itself? How many times going around a circle? I heard 6, I heard 5. So I could map it like this petal onto this one, onto this one, onto this one, onto this one. So if I start here, I can go 1, 2, 3, 4, 5 to get back to the start. So yes, the order is 5. And then the magnitude would be 360 divided by 5. Did anybody calculate that angle? 72. So that smallest, that first rotation, I'd have to go 72 degrees to map that, or map the petals back onto themselves, and then I could keep going 72 degrees until I get to 360. Now the flower in E is different. If you look at it in D, all of the petals are the same. In E, they are not all the same. Some of them are, but not all of them. This one still has rotational symmetry. If I pick this as my start, anybody know how many or what the order of this one is? It's not 6. It is 3. Okay, so when I look at this, I cannot map this petal onto this one. This petal is larger than this one. So these 3 petals, this one, and this one, these are all the same, and then these 3 are the same. So I could map this petal, I'd have to rotate it all the way to here as my first rotation, and then I'd have to rotate that to here, and then back to the original. So 1, 2, 3. So yes, the order is 3, and the magnitude then is what angle? 120. Okay, any questions right now on rotational symmetry? Can be a little harder to picture. And then the last 3, so these examples are just identifying plane and axis symmetry, but there is another type over here called point symmetry. I just want you to take a look at that. So a figure is said to have point symmetry if the figure can be mapped onto itself by a rotation of 180 degrees. So actually this flag here would have point symmetry. All playing cards, or I guess your typical playing cards, some might not hold true for this. A playing card exhibits point symmetry because if you turn a playing card upside down, it looks the exact same. So all playing cards have point symmetry if that center is the center of the card. Then we have plane symmetry. So a 3-dimensional figure has plane symmetry if it's mapped onto itself by a reflection in a plane. So this is different from line symmetry and rotational symmetry because you're working with 3-dimensional objects and not just the 2-dimensional figures we were looking at here. And then axis symmetry, a 3-dimensional figure has axis symmetry if it's mapped onto itself by a rotation between 0 and 360 through some axis. And these might be a little harder to picture. It's a little harder for me to kind of show because of the 3-dimensional drawings are kind of difficult. So in A, here you're stating if these figures have plane, axis, symmetry, both, or neither. So A, how you want to picture this is you have to picture, is there a way that I could slice through this object with a plane, or then when I slice through, both sides or both halves are the exact same. So here, if I took a plane and I sliced through this way, so your plane would kind of cut through exactly half of this, which I know this is going to be a terrible drawing, like I said. So I could slice through the exact middle of that, the exact center, like vertically, and then my two halves on either side of that wall would be the exact same. So this does have plane symmetry. I realize that's kind of sloppy there. That does say symmetry. So there's plane symmetry in A. Axis symmetry would be if you could draw an axis somewhere, if you could get the object to be itself just by rotating it about the axis. And usually for axis symmetry, it kind of has to do with rotational symmetry. It's helpful if some base or side of the figure has rotational symmetry for the object to have axis symmetry. So this one would not have axis symmetry, and it might make more sense seeing an example that does. If we look at B, would you say that B has plane symmetry? Is there a way you could slice through that object and have your two halves be the same? Yes. There's actually more than one way that you could slice through this and have that be true. So this has plane symmetry. It also has axis symmetry. So here's how I want you to picture that. I know that this pentagon that's on here, and again, this is assuming it's a regular pentagon. I know you're not supposed to assume, but this pentagon would have rotational symmetry. I could rotate like one vertex of the pentagon to the next, to the next, to the next, to the next, to the next. So if I drew like an axis through my figure, so you'd have a line that's like cutting through the center of this three-dimensional figure, and you're rotating the entire figure on or around that axis, that's kind of what you're picturing. So if I rotate it, it's kind of like, again, that rotation of just the pentagon. If I rotated the whole figure to here, then it would map the whole figure onto itself. So this one has both plane and axis symmetry for B. Would you say in C that baseball or softball glove has plane symmetry? I'm hearing some no's. I'm not sure if anybody said yes. I'm hearing some no's. I would also say no. Does it have axis symmetry? No. So this one has neither. And then what about the bat? Does that have plane symmetry? Is there a way you can slice through a bat and have both halves the same? Yes. Which way, based on how this is drawn, which way would you have to slice through it? Yeah, like going across, like through this way. So either like if it's laying down through this way or like this. Does it have axis symmetry? It does. If the axis went this way also, and you spun the bat around, it's going to keep rotating onto itself. So this has both. So that's what you want to picture for plane and axis symmetry.